Hi, today I want to tell you about using cranial endocasts as a proxy for frog brain size and shape. So some of you may have heard about a little thing called an endocast. A cranial endocast is basically a cast of the inside of the skull in the endocranial space where the brain would normally sit. Now, back in the day, they actually used to make physical endocasts out of latex, but these days we have CT scans. So we can digitally make a cast of the endocranial space without having to dissect or skeletonize a specimen. In this way, we can also add other information to our endocast. So in this particular case, I've used the grayscale values from my histogram to map colors onto this endocast that show where it touches bone and where it opens out into empty space. So we can visualize where there might be sutures or openings for nerves or blood vessels. The ultimate goal of using endocasts is to use them to better understand the neuroanatomy of extinct and extant species. So we can use them to take measurements and estimate brain shape and size without physically dissecting or staining a specimen. We can also create endocasts from a fossil where we don't even have any soft tissue. And we can use endocasts to take a lot of measurements and use these in a comparative way to make inferences about a whole bunch of things. So how well do vertebrate endocasts actually match up to their respective brains? Well, we know for mammals and birds, there's been a lot of really great work done to show that the size and shape of an endocast is actually a pretty good proxy for the real brain. But when it comes to reptiles, amphibians, and fish, the waters are still a little muddy. So I wanted to begin to address this. And I had to start somewhere. I decided I would start with frogs. Now, there's a pretty good reason that I wanted to start with frogs. Anyone who knows me knows that my main job is working on the oVert project, where I am CT scanning and contrast enhanced CT scanning all of the vertebrates. And we're nearly done with frogs. So we have done standard CT scans of over 96% of described frog genera. And we have done 95% of described frog families for our contrast enhanced soft tissue scans. So I wanted to get brains and endocasts for all of those 55 frog families. So I started segmenting, and consequently became lost in endocranial space. So this is an alternative title for this talk and a pretty accurate representation of what I did with a lot of my spare time during 2021. So I want to take you on a journey through endocranial space. So far, I've processed 30 different frog families. I'm still going, but I do want to show you what I've found so far. Here's an image showing a collection of different brains and endocasts of frogs. And you can see here that there is quite a great deal of variation in both shape and size for our brains and endocasts. What you'll also notice is there is some variation in the way that the bone encases that endocranial space. And you will see different numbers and sizes of openings on those endocasts. So I want to take you on two different legs of this journey. The first is looking at some data to see how well brains and endocasts actually match up to each other. The second is a plot twist in the form of the endolymphatic organ. More about this later. All right, so let's go embark on the first leg of our journey through endocranial space, comparing brains and endocasts. So here I've shown two equivalent versions of the CT scan. So on the left, you'll see a slice through lengthways through the body of a frog, of a standard CT scan of that frog, where we can see the skeleton. And you'll see that I've started building my endocast by filling in that endocranial space there in yellow. On the right-hand side, you'll see the contrast enhanced version of this CT scan with the brain highlighted in purple. And you can see that the brain actually doesn't take up all of that endocranial space. So I took my brains and endocasts and I measured their volumes. And I found they actually match up pretty well. So there's a pretty tight relationship between endocast volume and brain volume. A strong positive relationship with a high R-square value. So we can be pretty confident in estimating brain volume from endocast volume. When it comes to the percentage of the endocranial space that those brains actually occupy, it ranges from 18 to 63%. Now, not only is this on the lower end of the scale compared to birds and mammals, but this is a pretty large amount of variation. So I wondered why this was. And at first, I thought it had something to do with size. And I thought this because as I started adding brains and endocasts to my data set, the smaller brains seem to be the ones taking up a larger percentage of their respective endocranial space. But the more data points I added, the weaker this correlation got. So there is a significant but weak correlation between these two things. So clearly there's some other factors at play here. And I want to tell you about one of these. So the next leg of this journey is a plot twist in the form of the endolymphatic organ. So here you can see a CT slice through the middle of Brachycephalus's head. In the endocranial space, where we would normally be building our endocast, you can see these structures. It looks like some kind of deposit. It's very dense, so it shows up in both CT scans and contrast enhanced CT scans. And it turns out it's this stuff called endolymph. So endolymph is a calcium carbonate deposit in an endolymphatic sac. And you can see it rendered here in blue in Brachycephalus, how it's deposited inside the brain case. Turns out this endolymph is pretty common in frogs. Out of the frogs I've processed so far, I found that endolymph was present in over 50% of them. So what do we know about this endolymphatic organ? Let me tell you. We humans have one. It's a tiny little sac inside of our ear, and it's involved in immunologic defense. Geckos have one. Geckos have endolymphatic sacs behind their head. These ones are also full of calcium carbonate deposits, and these are depleted during and involved in egg development. But what do we know about this endolymphatic organ in frogs? Turns out not that much. I thought this was going to be easy given how commonly I was finding it in frogs, but I'll tell you what we do know. So from a clinical perspective, we know what it looks like in an X-ray. It's very dense. It can show up as these nodules, and it can be distributed inside the brain case, around the brain, and along the spinal column. From a morphological perspective, we have this paper from 1930 where they describe 6 morphological types of endolymphatic organ in amphibians, with 2 of these occurring in frogs, as you can see examples of in Bufo and Rana. The problem with this is that they made these observations using 4 different frog families. There are 55. From a functional perspective, we also know a couple of things. These deposits are involved in the ossification process. So during the development of a frog, when it's building its skeleton, calcium is mobilized to different parts of the body. But these deposits persist after the skeleton has been built throughout the life of the animal. So we know that they're probably involved in something else too. So now I want to tell you a little bit about what I have seen. So this is a CT scan, or a combination of a CT scan and a dye-CT scan of a rosy ground frog. And you can see the calcium deposits rendered in blue and how they are distributed around the frog's brain and along its spinal column. Now, I can tell you from processing a lot of frogs that there is a large amount of variation in both the amount of these endolymphatic deposits and the way they are distributed. So here are 6 different examples of frogs that have endolymphatic deposits. And I want to point out a few things. Some of these frogs have a lot. Some of them have a little bit. Some of them, which I've not pictured here, have none at all. And the way it is deposited differs in a couple of ways. You might see it as teeny tiny little blobs. You might see it as rather large nodules. Also, you may see it distributed mostly along the spinal column. You could also see it mostly inside the brain case, and sometimes a lot in both. So naturally, I wondered how this endolymphatic organ affects the size and shape of my cranial endocasts. Now, you may think, as I did, that the presence of this endolymph would make the endocast an overall better fit for the real brain. But it turned out this is not necessarily the case. And in fact, some of the frogs that take up the least amount of endocranial space also have endolymph present. Now, these are some heat maps. These are heat maps of endocasts, which show how well they fit around their respective brains. And you will see from the frogs that have endolymph present, if you look at those locations where there is endolymph, that makes those areas of the endocast a better fit for the real brain. Next, I want to talk a little bit about, and mostly just speculate about, what the role is of this endolymphatic organ in frogs, other than building skeletons. At first, I thought it had something to do with hyperossification. And I thought this because the first few frogs that I processed and found endolymph in also happened to have hyperossified skulls. But alas, as you can see here, I have since found it in hyperossified and underossified skulls alike. One strong suspicion that we have is that it has to do with reproductive strategies. It's kind of like in the gecko. So this is a teeny tiny Seychellophrine frog that has a large amount of endolymph along its spinal column. And it also happens to be full of eggs. So perhaps these two things are related. This is a frog that has the most amount of endolymph of any frog I've seen so far. This is Stefania. It's also known as the carrying frog. And it's called the carrying frog because this frog carries its babies on its back while they develop. And not only do they develop, they fully develop. So by the time the baby frogs jump off the back of the mother frog, they have fully formed skeletons. So perhaps the endolymph is also involved in building the skeletons of the baby frogs too. Lastly, I want to show you the pumpkin toadlet. So Brachycephalus here has a very highly ossified, not only skull, but skeleton too. And its skeleton glows under ultraviolet light. Has this anything to do with endolymph? Maybe, probably not. Mostly I just wanted an excuse to show you that Brachycephalus exists. Clearly, we need to better understand how the endolymphatic system affects brain and endocast shape and size in order to better understand frog neuroanatomy. So I'll keep working on that through 2022. Thank you to all of these people for their involvement in this project, and I'm really happy to take any questions if you have them.